Okay, good morning, everyone. Let's continue with our discussion of AC analysis. Okay. Let me make sure I have the right share. All right. Okay, so any questions about anything we have done so far? Right. So why do we use sinusoidal shapes? Well, that's the most common voltage or current form that we have today. All AC power that we receive from our power outlets, whether in the homes or commercial spaces, is all sinusoidal in shape. Okay, a sinusoidal current or voltage is very easy to generate. As I mentioned in last class, you can have a generator spinning inside so it's basically a coil of wire spinning inside a rotating magnetic field, passes through the north and south pole, and the generated electrons, well, the shape of the electrons and the value of the current is basically sinusoidal in nature. And then through various different kind of mathematical tools, you can represent any kind of AC waveform as a multiple repetition of sinusoidal waves. Okay, so you could take a square wave, a triangular wave, ramp, sawtooth, rectangular pulse, any kind of AC waveforms, and you can represent it all mathematically as a sinusoidal waveform. And then since we are dealing with capacitors and inductors, we have to perform derivation and integration, solve differential equations. Well, the derivatives and integrals of a sinusoidal waveform are also sinusoidal in nature, right? Sin x and cos x. Derivatives and integrals of sin x and cos x are basically sine and cosine. And so it makes it easier to handle it mathematically. But more importantly, in the analysis, the mathematical tools that we use, we can represent each of these sinusoidal waveforms as a vector in the complex plane. And we can apply complex numbers and complex math to actually reduce our circuits. Well, not reduce, but to reduce the math of our circuits from differential equations to simpler circuit analysis problems. Okay, so we saw in chapters 3 and 4 how we would have to deal with differential equations to solve for the voltages and currents. When we apply the vector math or the complex math, we can reduce the math to simple circuit analysis problems. So all of the techniques that we learned, KVL, KCL, for instance, they all apply equally just by using complex number math. And sorry about that. All right. So when we apply a DC voltage or current to an inductor or capacitor, after some point of time, it reaches steady state. And so is the case with AC. Even though the AC voltage or current is fluctuating between a positive and negative peak or between two numbers, there is something known as a steady state response. Okay, and that steady state response is what we are interested in. Okay, now okay. So now when we are trying to solve for the voltage and currents for an inductor, capacitor, or resistor, we already established, or we already know that a resistor does not have any energy storage capabilities, right? So since it doesn't have any energy storage capabilities, the response of a resistor to an AC voltage or AC current is exactly the same as it was for DC. Okay, so resistors are exactly the same. Same as DC, as well as for AC. Inductors and capacitors, and again, I mentioned this at the beginning of the chapter, we are required to solve differential equations for L and C. So we use a technique where we represent all components in a circuit as vectors using complex numbers. Okay, that's where we talk about phasors and impedances. Okay, phasors and impedances. They are both represented using complex numbers. Now, these phasors, unlike the ones from Star Trek, are not going to stun you or kill you, but they will scramble your brains. But overall, the circuit analysis is much simpler. Now, there's phasor, there are transforms and derivations of how it comes about. That's not something that we go into in this class, but I will give you an overview. What we do is we take our sources. The source could be a voltage source or a current source. Sources would be a function of time. And we do a phasor transform and represent it as a vector in the frequency domain. And so the symbol is kind of like this. Now, in a book, it's easier to actually recognize what the symbol is. I just use like, two short dashes on top of a uppercase V. And I of t would be represented with uppercase I. And again, I just put small notations on there. So what we do is we transform the time varying signal, the time varying expression into a complex number. And that is one of the reasons why we keep the phase of the signal separate in the mathematical expression. And then inductors and capacitors are represented by complex number or complex quantities known as impedances. Okay, and we'll look at each one of those quantities in the next few slides. So again, the four components that we look at: sources, both voltage and current, and then the resistors, inductors, and capacitors. All four of these components are represented mathematically using complex numbers. Okay, complex number math. So what is a phasor? Phasor is simply a rotating vector in the frequency domain that represents a single snapshot of the sine wave function. Okay, it represents a single snapshot of the sine wave function. So below here, we have the time domain representation, right, where we describe the value of that quantity as a function of time. That quantity can be voltage, can be current. Here we use voltage V of t, right? And we already saw this expression. V of t is equal to Vm cos of omega t plus or minus theta. Okay, theta can have both positive as well as negative values. Now this expression is still the same, whether you use sine or cosine. So it could be Vm sine omega t plus or minus theta. The relationship between sine and cosine, of course, is sine x is equal to cos of x minus 90 in terms of degrees. Okay, in terms of degrees. Oh, sorry. And this is very important to remember. I'll come back to it in just a few seconds. So we have the time domain representation. The peak value of that waveform is Vm, or the magnitude of the waveform, or Vp, if you will. Again, as a reminder, Vm is the peak value. The M stands for magnitude. And the reason we use M, or this author uses M, is because we represent it as a vector. The vector has magnitude and direction. Magnitude as well as direction. So if you look at this frequency domain representation with a rotating vector. You can see the snapshot is showing you two things. The length of the vector, which is Vm, and then the angle it makes with the real axis. That angle is the phase difference. This is the phase difference. If the sine waveform started at 0, 0, okay, if the sinusoidal waveform started at 0, 0, then the phase would be 0. The vector would be lying on the x-axis with a phase angle of 0. Does that make sense to everyone? Right? If the sine waveform, the sinusoidal waveform, began at 0, 0, right here, then the phase or the phase angle is 0 degrees. And the vector would simply lie on the x-axis. And this is the vector Vm. So the point at which the waveform crosses the x-axis right there, that gives you the projection. The distance from 0, 0 of the sine wave gives you the phase, and that phase is the phase angle of that rotating vector. You can describe this vector with only two things, the magnitude and the phase angle. So you can directly write down the phasor form of a time varying signal with only two things, Vm and then theta. That's it. Those are the only two things you need. Omega, which is included in the time domain expression, which describes the frequency of the waveform, right? In the time domain expression, you have omega, is not used for the vector. The vector needs only two things to describe it, the magnitude and the phase angle. Okay, magnitude and the phase angle. So simply Vm with a phase angle of theta. If it's current, the phasor for I can be written as Im, the phase angle of theta, whatever that angle value may be. Omega is not part of that description. Omega is the speed at which the vector is rotating in the frequency domain. Okay. Now, one important thing is that if you wish to write the phasor directly, the time domain expression must be in cosine. Let's see. The equation must be in cosine, not sine. So if you have a description of a voltage or a current which says sine omega t, you have to subtract 90 degrees from the phase to make it cosine. This is a sine wave. And let's see. And this would be cosine. Okay. Each full cycle is basically a rotation of 360 degrees. So 1t, one full time period, meaning going from the positive peak to 0, negative peak, and back to 0, is 360 degrees, or 2 pi. Each half cycle one t is full cycle. Half cycle is 180 or just pi. And the difference between sine and cosine is pi by 2, which is 90 degrees. So again, this expression is very important. If you need to write the phasor transform directly, and if your expression is in sine, you must change the sine to cosine before you can write the phasor directly. The sine omega t becomes cos of omega t minus 90 degrees. Okay. All right, 10-second pause. Let me know if you have any questions. So far, so good. Well, we won't need to for this class, but then again, there are so many trigonometric identities that, I can have a list if you want, but we just add 90 degrees in that case if you want. For the most part, when we do an example, it'll always be in cosine. If it is in sine, then we go back, or not go back, we change it to cosine, we write the phasors, we do our calculations, and at the end, we have to write the time domain varying expression. It has to be in cosine. There would not be any need to go to sine. Okay, impedance. So that was for the sources, meaning if you have a voltage source or a current source, you express it in cosine and then simply write down the magnitude and the phase angle to describe the source as a phasor. Impedance, for the most part, I would say, is analogous to resistance, but technically that's not correct. Okay, technically that's not accurate. Impedance is a vector quantity, again, represented using complex numbers. Oh, one more thing, just about complex numbers. So this phasor is described as a vector Vm with a phase angle of theta. The projection of this vector on the real axis and on the imaginary axis gives you the rectangular coordinates, A and B. So Vm phase angle theta would be A plus or minus JB, where J represents the imaginary number I, because I is used for current in EE. Okay, so rectangular coordinates, it is A plus or minus JB. J is the imaginary number in electrical engineering. Okay, so impedance. Impedance, resistance, reactance, they all are kind of synonyms of each other. They all work similarly because they are opposition to something. Okay, resistance comes from resist, right? You're opposing the flow of current, opposing the establishment of voltage. Impedance comes from impede. You're impeding or opposing the flow of rate of change of current or the change of voltage in the circuit. Okay, so they are all kind of synonyms of each other, but the technical description is that the impedance is a vector quantity. It comprises resistance and a reactance. Mathematically, we represent resistance using real numbers and reactance with imaginary numbers. So impedance is noted by the letter uppercase Z. Resistance, you are familiar, uppercase R. Reactance is uppercase X. And the vector quantity is R plus JX. Important to keep in mind, anytime we use imaginary numbers to represent something, that quantity is not imaginary in real life. Okay, it has a physical basis, it is real. We are simply using imaginary numbers to represent it. So if you read that this quantity is imaginary, it does not mean that in real life it is imaginary. It is the number, is the math that we are using that makes it imaginary. Okay, so that reference is simply for the math. Is that clear to everyone? Hopefully, yes. Okay, so what exactly is impedance and reactance? Well, resistor has resistance, right? We already saw all of that in chapters 1 and 2. Capacitors and inductors, at least ideal capacitors and ideal inductors, do not have any pure resistance. Okay. Now, real life inductors do have resistance, but ideal inductors, the resistance R is equal to 0. Okay. So if you are trying to describe the impedance for a resistor, it would simply be R plus J0, which is simply the resistance itself. Okay, so the impedance of there's no such thing as an impedance of a resistor. A resistor behaves exactly the same way it does for DC and AC. Okay, it behaves exactly the same way. It resists the flow of current. Now, capacitors and inductors have an electromagnetic field and an electrostatic field where they store the energy. When you apply a constant DC voltage or constant DC current, electrons are only going one way. So energy is only being transferred one way. The capacitors and inductors receive the energy, they reach a constant state or steady state, and then that's it. In an AC source, when you apply an AC source to a inductor or capacitor, the energy is constantly flowing in and out because the electrons move back and forth. So the energy flows in and then it flows out. For a inductor, if you have a waveform like this is the positive half cycle, this is the negative half cycle, and this is the positive half cycle again. For an inductor, in the positive half cycle, energy flows in. So energy in. And for a capacitor, it goes out. In the negative half cycle, for an inductor, the energy flows out. And for a capacitor, the energy flows in. Again, for the positive half cycle, energy flows in. For a capacitor, it flows out. Capacitors and inductors are duals of each other. They are very similar, but they're exactly opposite in many ways. Okay. And it works out beautifully for applications. So again, for an inductor in the positive half cycle, the energy is going to flow in. In the negative half cycle, the energy is going to come out. Capacitor is the exact opposite. So when you have a magnetic field in an inductor, that magnetic field gives rise to a voltage that opposes the initial voltage due to the applied current. And that opposition can be described in terms of the reactance. Okay. When you apply an input current to an inductor, it causes a voltage drop with polarity in one direction at the point of entry. It sets up a rotating magnetic field. It sets up a magnetic field. And then magnetic field gives rise to an opposing EMF or an opposing voltage that resists any change in the input current. And that quantity or that opposition is described by the term reactance. Okay. And because all of these are opposition to something, the units for all three are the same. The symbols for all three are also the same. They all use the same symbol that we used for resistors and the Greek letter omega or ohms. Okay, so impedance is also in ohms, reactance is in ohms, and resistance is also in ohms. So again, reactance is the opposition to the change of current that is initially being applied to that inductor or that capacitor. Okay, so that's where reactance comes from. This reactance is important because in industrial applications, when you have electric machines, they require some power associated with that reactance, which is known as reactive power, which is something students would do in the lab in lab 8. Okay. Anyway, coming back to our point. Questions about reactance. Again, it is opposition to the change of current that is flowing through the circuit or through that component. Okay. It's a complex quantity. So impedance Z is described by the real resistance and the imaginary reactance. All right. If you take the three quantities, R and Jx, R resistance lies on the real axis, so it's on the x-axis. Impedance X represented by the imaginary number I, so it's on the y-axis. And the third side of the triangle gives you the impedance, Z. Again, it's a complex quantity, so you can describe impedance with rectangular coordinates or polar. Again, it can be represented as a vector with magnitude and the angle. Okay, so if you're given resistance or reactance, right, resistance and reactance, you can transform it back and forth between polar and rectangular coordinates. You have magnitude of the impedance and you have the phase angle of that impedance. And that is known as the impedance triangle. Okay, impedance triangle. Z equals R plus JX gives you the impedance triangle. All right, 10-second pause. Let me know if you have any questions. Any questions at all? Okay. All right, so then let's look at impedance for an inductor. As I said, ideal inductors do not have any resistance, so it's 0 plus JXL. X is the reactance, and for an inductor, XL is given by omega times L, the value of the inductance, and omega, of course, is 2 pi FL, where F is the frequency in hertz of the incoming signal. And ZC similarly is 0 minus JXC, where XC is 1 over 2 pi FC. The reason it's minus, you can write it as 0 plus 1 over J XC. One over J is minus J. Okay, so those are the equations in terms of the frequency. Again, XC is actually, it's 1 over omega C, 1 over 2 pi FC. Omega is 2 pi F. Do not forget that relationship. Now remember, at the beginning of this chapter, I talked about phase difference between waveforms. Well, here's where it becomes important. For a capacitor and an inductor, the voltage and current are not in phase. Okay, they do not have the same value at the same point in time. They're out of phase. Okay, for a resistor, there is no difference. But for a capacitor and an inductor, there is a phase difference of 90 degrees. So if you take the voltage for an inductor, voltage leads current by 90 degrees. So that means theta V minus theta I is equal to 90 degrees. For a capacitor, it's the exact opposite. Voltage lags the current, or I could say current leads voltage by 90 degrees. So theta V minus theta I for a capacitor is minus 90 degrees. That's where the minus sign comes from for the impedance of a capacitor. So voltage is ahead of current for an inductor, and current is ahead of voltage for a capacitor. There's a phase difference. And that is always true for any capacitor and any inductor. Does not matter the value, does not matter the circuit conditions. Nothing else matters, but the voltage and current phase difference of 90 degrees always remains the same. Okay, so this is an important concept to keep in mind, because when you're solving problems, you can verify your answers by using this relationship. Now, we have transformed and represented both our sources as well as components as complex quantities, right? So the whole point of performing this transform is we can apply our circuit analysis techniques techniques to AC circuits, so that we don't have to solve differential equations, right? So all of the laws that we learn, Ohm's law, KCL, KVL, node voltage analysis, mesh current analysis, everything still works. Everything is still applicable, except that the quantities now are complex quantities, and so you have to take the phase angles into account. So Ohm's law, which was V equals IR, is still valid. It now becomes V equals IZ, right? V equals IZ, total impedance of the circuit. If you're working simply with the average values, you would take IX. So it would be V is equal to I times X if you're using RMS values or average values. So for a resistor, a particular resistor or a specific resistor, you apply Ohm's law, it becomes IR, the current for that resistor, times R. Inductor VL, the inductor voltage VL, is simply IL times ZL, the impedance of that inductor. You do not have to apply the equations that you learned in chapters 3 and 4. If you think back to chapter 3, inductor voltage VL is L di over dt. Remember that? And then inductor current IL was the integral of VL. So it becomes very complex or very difficult very, very quickly. But because of the transform, the phasor transforms, and using complex numbers, we can simply apply Ohm's law. You can solve it using the differential equations, or you can solve it using Ohm's law, your choice, right? But again, the whole point of doing this, of using complex numbers, is to make the math less complex. And similarly, of course, VC can be found using simply IC times ZC. Simply apply Ohm's law. KVL still works. If you have a loop, electrical loop in the circuit with multiple components, you add up all the voltages, they should sum up to the source voltage, or they should sum up to 0. Same thing with KCL. All currents entering a node have to equal all currents leaving the node. Everything still works, except that the math is now using complex numbers. All right, let's take a 10-second pause. Think over that. Let me know if you have any questions. Any questions at all? Does all of this make sense? Hopefully. Let's see. Oh, by the way, I have a practice sheet on the website under slides, complex number math. If you can't find it, you let me know. What each and every student needs to do is become an expert, or at least be adept at using their own calculator devices to perform complex number math. Okay, that is not something that I would be able to help you with. My calculator is from the 90s, so it does not have any programmable functions. And it does, I can do polar to rectangular conversion, but I cannot program equations in there directly. So I have to do the math manually in there. If you have a calculator like that, you would need to transform between polar and rectangular coordinates. Or if you have a programmable calculator like the TI-83, TI-84 perhaps, you need to be able to program equations directly in there, and it would give you a direct answer. But again, every student needs to be adept at using their own calculators for this. And again, this is not an electrical engineering thing, it's an engineer thing. So some of you may have already used this kind of math for some of your other classes, perhaps, or you may encounter it again. So it's not a skill that's only for this class, okay? So when I was talking about that, it's here, polar to rectangular conversion, polar to rectangular math. You have a vector with a length of r, phase angle theta. The projection of this vector on the real and x-axis gives you the rectangular coordinates. If you're performing math, as we will do when we apply Ohm's law, for instance, or you apply KVL, you're either performing a multiplication or division, subtraction, addition, lots of things. If you are performing addition or subtraction, you can easily do that in rectangular coordinates. If you're multiplying or dividing, it's easier to do in polar coordinates. Show of hands of how many of you know how to do this? Kind of. Yeah. And of course, you can perform any mathematical operation using any coordinate system, but it's just easier in some ways. So if you have A plus or minus JB, performing addition or subtraction with another, the real numbers add up. So it'll be A plus or minus C plus or minus the real, the imaginary. So you would add or subtract the real components, you would add or subtract the imaginary components. If you're performing multiplication and you have polar coordinates, A with a phase angle of theta B multiply by B with phase angle, not B, sorry, C, the phase angle of D, then the magnitudes are multiplied and the phase angles are summed up. So if you're doing Ohm's law, V equals I times Z, and you have polar coordinates, you can perform this math. And if you perform division, the magnitudes get divided and the phase angles are subtracted. Numerator minus the denominator. So theta B minus theta D. Okay. Now, in most cases, as I said, if you have a calculator that can multiply, let's say, polar coordinates with rectangular, all you need to do is program the equation. It'll give you an answer. If you have a calculator like mine, again, from the 90s, then you can't. So you have to perform the conversion back and forth. And I'll show this to you when we actually get to examples. This is also the reason why we have a negative for the capacitor impedance. Okay. Capacitor impedance is negative. It's the magnitude is fine, but the phase is exactly opposite to that of an inductor. So if you had ZL, there would be magnitude for the voltage. It would be VL or IL. Magnitudes would get divided, but the phase angles are subtracted. And we know that the voltage for a inductor is ahead of the current by 90 degrees. So this comes out to be plus 90. For a capacitor, it's the opposite. VC or IC, where voltage lags the current, or the current is ahead by 90 degrees. So when you do theta V minus theta I, you get minus 90 degrees. If you plot it up, then the impedance for an inductor is pointing straight up. Impedance for a capacitor is pointing straight down. We are 180 degrees out of phase. Plus 90 and minus 90. But it's specific to that capacitors, okay? Specific to that capacitor, specific to that resistor. You could have multiple components in a circuit. You could have a source, resistor, inductor, capacitor. They could be connected in series, in parallel, or any other way that we saw in chapters 1 and 2. And the phase could be, let's say phase for inductor is like 45 degrees or minus 78 for the voltage. Then the current would always be 90 degrees behind that value. So minus 78, minus 90. So the difference between the two would always be 90 degrees. All right, any questions? Again, there is a practice sheet, practice worksheet. If you are not comfortable using your devices, download that sheet from the website and then perform those operations until you become comfortable with it. Any questions? All right, impedances and reactances, like resistors, add up the same way. And do not confuse impedance of an inductor and the impedance of a capacitor with the value of the inductor and the value of the capacitor. Okay, an inductor, the value of the inductor adds up the same way as resistors, but when you transform this and we are talking about impedance of the circuit, then the impedance of an inductor is simply represented by that resistor symbol, right? ZL. And so is the case with a capacitor. ZC. So if you have a circuit, for instance, where you have a inductor connected to a capacitor, L and C, there is no reducing these components. They are two different components. But when we talk about the impedances of these components, it's ZL and ZC, we can find the equivalent in impedance between the outer two ends. And we say that they are in series and the impedances can be summed up. So ZEQ would be equal to ZL plus ZC. They add up the exact same way as you add up resistors in series. And if they were connected in parallel, they would add up the exact same way that you would add up resistors in parallel. Okay. Again, if you have resistors, inductors, and capacitors all in the same circuit, a resistor stays the same, but you can transform the inductor and the capacitor into an impedance, and you can find the equivalent impedance ZEQ at the outer terminals, which is what we will do in the examples. Okay, you can have multiple components, you can combine the impedances. You cannot combine an inductor with a capacitor, but you can combine the impedances. Does that make sense to everyone? All right, and final slide about the quantities. These we are not going to see in 201. You would have come across this in 251. There are terms that we use to make our calculations slightly easier. So they're all reciprocals of each other. Okay, the reciprocals of impedance, resistance, and reactance. Okay, again, impedance comes from impede. So we have a reciprocal for impedance, which is admittance, which comes from admit. Resistance comes from resist. The reciprocal of resistance is conductance. Resistance is opposition to the flow of electrons, right? Flow of current. Conductance is basically the permission or to permit the flow of current. And then reactance, the reciprocal is susceptance. The notations are there in parentheses at the end. So Z, R, and X is 1 over Y, 1 over G, and 1 over B. Reciprocals. And the units for Z, R, and X are all in ohms. Reciprocal for the admittance, conductance, and susceptance is named after the German physicist Siemens. At least I think he was German. I'm not really sure, right? Yeah, German. For a time, I've also seen Mohs, which is simply the opposite, or the reverse order of ohms. I've seen that too. But anyway, you would see this in the lab where we have a parallel circuit, and it's easier when you have reciprocals because you simply add them up, right? If you have a parallel circuit and you're trying to add up the impedances, it would become ZEQ for parallel would be 1 over ZR plus 1 over ZL plus 1 over ZC. If you already have the reciprocal, you know that 1 over ZEQ would be YEQ, admittance, and it would simply become YR plus YL plus YC. So the math is a little easier to deal with. Nowadays, it does not matter so much because we have powerful calculation tools at our disposal. We have computers, we have smartphones, we have calculators that perform all these functions. So it does not matter as much nowadays. But again, in 201, we will mostly just deal with impedance, resistance, and reactance. All right, we'll end class here today. Next class is all about example problems. So we'll solve the example problems 1, 2, 3, 4, or 1, 2, and 3, I believe. No, 1, 2, 3, 4, and then 5. Yes, 1, 2, 3, 4, 5. All right. If you have questions, I'm around. Otherwise, I'll see you all on Friday. Homework was due tonight, but I moved it to tomorrow night, Thursday night. But again, the homework 15 is all based on the topic that was covered, the material that was covered on Monday. So that is, that's sufficient time to get everything done. All right. See ya.